before that, just you have to see here. Okay, once again, just I have to repeat it, the definition. That is cyclic group. What is the cyclic group? Suppose let G be any one of the group. In that group multiplication or whatever it is, any one of the binary operation. Here G under multiplication be a group, and here small a belongs to capital G. A B, only one of the element must be generated in the base part, and all the integral power of the elements must be represented in the as in the power. Now that is the power of the elements is denoted by, now those elements are integers. Here that is a power 0, a power 1, a must be generated here. Okay, only one element through the integral power of the elements. That's why here a must be the generated by an element of a group. Now that is called a cyclic group definition. Very important definition. It is simply generated by an element of a group is called a cyclic group. Here G must be a finite group. Here A is only one of the element. Here N being a positive integer. Now such that here a power 0 means that is the 1. 1 be the identity element in the multiplicative identity, and a power 1, a square, and so on. A power n minus 1. Just we are taking the element 0 to n minus 1. That's why here n being a positive integer. So here G, capital G under multiplication be a cyclic group. Now that is the simple definition. Cyclic group is generated by an element of a group is called, that group is called a cyclic group. That is very simple concept here. Now these elements are all distinct. Okay. Hence the group here, group of the elements is denoted by set of a power 0 must be identity, a power 1, a square, and so on, a power n minus 1. Now generated by the group is denoted by bracket of A or set of A, whatever it is, small bracket of A. Now it read as generated by an element of a group is called a cyclic group. Capital G equal to box of A or set of A or small bracket of A. That is the cyclic group notation. Okay. Now it is simply here capital X be any one of the subset of a group capital G. Now in that group, subgroup, smallest subgroup of G, it is containing a capital X. Now that must be the generated by capital X. Is denoted by bracket of X. Now that is the singleton X. It is called a singleton set, means capital X equal to here A B any one of the element that is generated A of this part. Okay. Now there are so many examples in a cyclic group. Now just you have to please note down, students. Please note down. Imaginary, find the generators of a cyclic group. Find the generators of a cyclic group. An imaginary of 4 groups of unity. Find the generators of a cyclic group, capital G, be an imaginary of 4 groups of unity. Okay. Please note down. What are the generators? In a cyclic group, there are particularly 2 generators in a cyclic group. That is 1 and minus 1. What are they? There are 2 generators in an infinite cyclic group. There are 2 generators. That is 1 and minus 1. This is also one of the important bit is there. Now it is very short. 2. That is one of the fill in the blank. How many generators in a cyclic group? There are 2 generators. Suppose it is completely based upon the order. Suppose capital G under multiplication be a group. Now it is in an infinite cyclic group of order is n. Infinite cyclic group of order is n. Now, how many generators? There are pi of n generators in a cyclic group. Now that is also one of the important debate. And in imaginary of 4 groups of unity means capital G equal to, please note down, capital G equal to 1 minus 1 I minus I. Okay, please note down. Imaginary of 4 groups of unity is capital G equal to what are the elements? 1 minus 1, 1 minus 1, I minus I. That is the 4 and 4th roots of unity. 4 and 4th roots of unity elements. Okay. What are the generators in a cyclic group? Please note down. What is the relation here? Particularly 1 minus 1, I minus I. 1 can also be written as 1 into 1. Okay, I power, we know that I power 4 equal to 1 is there. Okay, I power 4 equals to 1 is there. So, what are the generators? I can also be written as 1 means I power 4 minus 1. What is the minus 1? I whole cube. Okay, I square equal to minus 1. Second element minus 1 can also be written as I square. I can also be written as I power 1. Minus I can also be written as minus I whole cube. Okay, minus I whole cube means minus I. That is minus I into minus I into minus I. So I square is minus 1. Minus of minus 1 is, now minus into minus plus 1. I square is minus 1 into minus I. That is also plus I. So I cube is, that is value is minus 1. I cube equal to minus 1. Just we have to observe here. Now in the imaginary of fourth roots of unity elements, 1, minus 1, I, minus I. That is the group of the elements. Okay. Here multiplication as the composition. See, under multiplication, be a group under multiplication. Under multiplication. Okay. Now here 1 be the multiplicative identity. Multiplicative identity is 1. Now in the group of the elements can be written as 1 can also be written as I power 4. In the set of the element, just you have to update here. Capital G equal to 1 can also be written as I power 4. Minus 1 can also be written as I square. I is I means I power 1. Minus I can also be written as I cube. Okay. Now just you have to see here 1 minus 1 I minus I to be written as on the generators. I power 4 means 1. 1 equal to I power 4 comma I cube means minus I square minus 1, I power 1 is I. So here I is repeated as in the base part. Okay. Now 1 minus 1 I minus I elements can also be written as I square, I cube, I power 4. Now this is I must be generated is on the base part. Okay. Integral power of the elements is 1, 2, 3, 4. There are integral power of the elements. Those are. Okay. Now here I must be generated. Generated means this is. Just you have to see here. Okay, it is too clear here. Okay. Capital G equal to less than, greater than. In between, just you have to note down the less than I, and then after that greater than. Now it read as generated I or bracket of I or square bracket of I, whatever it is. Generated by an element is here small I. One of the generator is I. And the second one, capital G equal to minus I, comma, minus I whole power 1, comma, minus I whole square, minus I whole cube, minus I whole power 4. Okay. Minus 1 means, minus 1 whole power 1 means minus I. Minus I whole square means minus whole square is plus and I square is minus 1. Minus whole cube. What is the minus I whole cube? Minus I into minus I into minus I. So this is the I square minus 1 into minus I is minus 1 into minus I is plus I. Okay. Minus I cube minus I whole power 4. That is I power 4 is 1 is there. Okay. Now here the given this part imaginary of fourth roots of unity is capital G equal to 1 minus 1 I minus I. Okay, just you have to see here. Capital G equal to 1 minus 1 I minus I. Here G under multiplication be a group. Here one of the generator is small I. That is in less than and greater than, in between notated as I notated as less than and greater than, in between I notated as less than and greater than. So it read as generated I or set of I or box of I, whatever it is. Now it read as generated by an element is I. And second one is, and another element is minus I. Minus I whole power 1 is minus I. Minus I whole square is minus 1. Now group of the elements are, is it a group of the elements or not? Minus 1 is also one of the element given in G. Minus I whole cube is small I. Minus I whole power 4. That is also 1. So same elements given in the group. That's why here minus I is repeated. Now that is the integral power of the elements is 1, 2, 3, 4, and base the element is minus I. That's why here minus I must be generated. Now there are two generators in a cyclic group, four groups of unity. Capital G equal to 1 minus 1 I minus I, or I and minus I. I can also be written as, again, I can also be written as I into 1. Minus I can also be written as I into minus 1. Okay. Now here the generators I and the minus I, and unit generators are 1 and minus 1. There are two important, the number of generators in a cycle group are 2. How many generators? There are 2 generators in a cycle group. What are they? 1 and minus 1. That's enough. In 4 groups of unity, I is one of the generator and minus I is also one of the generator. It is denoted by less than I, and then after that greater than. Now it read as I must be the generator or box of I. Minus I is also one of the generator in a cycle group. And in the same manner, 4th roots of unity. This is the 4th roots of unity elements. And cube roots of unity is, what are the generators? In your cube roots of unity elements is capital G equal to set of, please note down, in your cube roots of unity, what are the generators? Capital G equal to 1 omega square. That is the cube roots of unity elements. Since omega cube equal to 1, that is the cube roots of unity expression. Here 1 be its multiplicative identity. Here G under multiplication be a group. If it is a cyclic group, 1 can also be written as, that is omega cube equal to 1 comma omega square. Okay. It is the unique form is omega power 1 omega square omega cube. Now that is the given the elements is omega power 1 omega square omega cube. Now here in the set of the elements must be represented as, here omega belongs to capital G. Okay, that's why here omega must be, it's one of the generator. In a cube roots of unity, one of the generator is omega, and the second generator is omega square whole power 1 omega square whole square omega square whole cube, omega square whole power 1 omega square whole square omega square whole cube. Omega square power 1 means omega square whole power 4 means omega power 4. Omega power 4 can also be written as omega cube into omega. That is 1 into omega equal to omega. So omega power 4 equal to omega. Omega square whole cube means omega power 6. That is omega cube into omega cube. Omega cube into omega cube. Say this one. Omega cube into omega cube. So omega cube is 1 and 1 into 1 equals to 1. So omega power 6 value is also 1. Now in the cube roots of unity elements can also be written as set of omega square whole power 1 omega square whole square omega square whole cube. Here the generator is omega square. The base path is omega square, is also one of the elements given in this group. Therefore, there are 2 generators in a cube roots of unity, generated omega and generated omega square. Okay, there are two particularly elements in a cube roots of unity that must be generated. Now, it can also be written as the integral power of the elements set of omega square, omega cube. There are 2 generators in a cyclic group. Okay, now that is in the same, at any time, there are 2 generators only in a cyclic group. What are they? That is 1 and minus 1. Omega can also be written as omega into 1. Omega. Omega square. Okay, omega into omega, that is also generated here. There are two generators in a cyclic group, especially in a two groups of unity. There are those generators are omega and omega square. Okay, students. Now these are all examples cyclic group. Now simply generated by an element of a group is called a cyclic group. That's enough. An integral power of the element is set of a power n. Here n being a integer. Okay, generated a equals to set of a power n, because here n must be a integer. Now it is suppose a power n equal to e. When n equal to 0 here. Now this value a power n can also be written as a power n minus 1 into a. Now that value is a power n. When n is greater than 0. Okay, suppose n less than 0, this is a power minus 1 whole power minus n. Just you have to look at observed here. Now this is minus 1 is also there. Okay, that is in the particularly common generators are a power 1 and a power minus 1, because the negative integers, suppose here n being a integer, so minus 1, 0, 1, these are all integers here. Okay, now but in particularly a belongs to G. A be any one of the element given in this group, a power 1 and a power minus 1. Okay, or a power minus 1 and a. So the integral powers of the elements minus 1 and plus 1. Now there are two generators in an infinite cyclic group, 1 and minus 1. Suppose given the group of order is n, so now that the number of generators are pi of n generators. Okay, that's enough. Now just you have to see and verify this one. Okay. Now, in the smallest subgroup generated A, notated as in a smallest subgroup generated A equals to set of A power n such that n being a integer. Now, just you have to see and to write the definition of a cyclic group in an examination point of view. Now, that is very simple. That is not necessary in the same manner of textbook part. Okay. Now, simply generated by an element of a group is called say a cyclic group. Here, multiplication as the composition, A power generates set of A power n such that n being a integer. Now, there are two generators in a cyclic group. In addition, suppose in addition, A power n can also be written as n into a, because a plus 1 up to n times or n terms. Here, generated A in addition notation, that is n into a. In the multiplication notation, set of a power n. Here n belongs to z. In additive notation, A is addition of the binary operation. Generated a equals to set of n a. Here n being the integer. That's enough. Now here G be any one of the group. That the group of the subgroup is denoted by capital H. Now when G must be a cyclic group and subgroup is also a cyclic subgroup is there. Because the group is a cyclic group, that cyclic group of the subgroup is also called a cyclic subgroup is there. Now that is also one of the important theorem in cyclic subgroups. Okay, just you have to see and verify. There is no problem. Just you have to see the examples in Z under addition one of the group. It is a cyclic group. Here in addition means generated A equal to set of A power n can also be written as in additive notation is NA. Here n being the integer. Okay, it can be expressed as n into 1. So 1 be the one of the element given in this group, and the generated element in Z under addition is a cyclic group is generated 1. According to the n into 1, here 1 must be generated. Okay. Now, in the same manner, second example, suppose here n modulo of the elements. Please stay on the line. Okay. Say here. Okay. Well, please stay on the line. Okay. For any positive integer n, here Zn means n modulo integers with respect to addition modulo n. With respect to addition modulo n. Modulo means this is one of the special binary operation. And according to that, n modulo integers is represented as 0, 1, 2, so on, n minus 1 elements. Okay. Now, under addition modulo n is also a cyclic group. Now, define a cyclic group. Give any example with briefly. Okay, there are two examples already well defined here: imaginary of fourth roots of unity and cube roots of unity, and addition modulo of integers is also a cyclic group. Now here the Zn generator is n addition modulo of the integers generated element is generated 1. Here 1 must be the generator. Okay, now order of 1 equal to here, because n modulo elements means that is the order is n. That is represented as cardinality of the group. What is the cardinality of the group? ORR, order of the group is order of an element is n is there, because here order of 1 equal to n or cardinality of Zn is there. Okay. Now here the number of here, what are the generators under addition modulo n? Only one generator in the addition modulo integers Zn equal to generated 1. Now in particularly 1 minus 1 I minus I can also be written as I must be the generator. What is the I power 4? That is the imaginary of fourth roots of unity element is already you have to explain here. I power 4 equal to 1. So that's why order of I equal to 4. There are number of elements given in the group is 4 elements. So that is the cardinality or mod G. Cardinality means mod G. Order of the group is O of G equal to the number of elements is 4. That's why this is the order. Now here I must be the one of the generator. In the same manner, minus I whole power 4 is also 1. So minus I is also one of the generator. So that's why here I and minus y both are generators in an imaginary of fourth roots of unity. In a cube roots of unity generators, omega and omega square, since omega cube equal to 1. Now, which is not explained, any suitable example is not a cyclic group. Okay. Now, one of the example is in a group Q of rational numbers, Q under addition. Okay, simply Q under addition is not a cyclic group. Why? Why it is? Now, here Q under addition is, suppose it is a cyclic, R be any one of the rational number. Suppose the rational number form is P by Q. Here R must be the generator in the rational number of this part. Now, in addition part, what is the in addition part? Set of NR. That is the notion is n into a. Here a must be represented as the rational part. Now n into a in additive cyclic group of the part. Now that is the n must be here a must be the generator. The n being the one of the integer. Suppose here r be its rational number. Set of n into r such that n belongs to Z. Suppose r not equal to 0. Okay, now here the P by Q form is R by 2 is also a rational number. R by 2 can also be represented as given in this set, NR. Here n being the integer. Suppose if in the cross multiplication we are getting the values 2NR is there. R equal to 2NR. Suppose 2n equal to 1 is there. What is the n value? 1 by 2. So this is a 1 by, suppose 1 by 2, n equal to 1 by 2. Now this is the contradiction of this part, because here n is an integer is there. Okay. Suppose Q under addition is not a cyclic group because there are no generators given in this cyclic group. That's why here Q under addition is that in particular Q under addition is not a cyclic group is there. Now explanation is here. Just you have to mention this explanation in examination. Okay. Define cyclic group. Give any suitable examples of a cyclic group means there are so many examples are already explained here, and any suitable example which is not a cyclic group means Q comma plus is not a cyclic group. That is simple expression. Okay, why it is now here? You suppose Q under addition is cyclic, just you have to write enter these 3 lines. Now that's enough. This is not a cyclic group because there are no generators. According to the addition of a cyclic group of the generated by a set is NR, because R being the generator of this part. But that is not satisfied, but particularly here n being the integer. Okay, that's it. Okay, is it a cyclic group? Yes. G equal to set of 1 minus 1. There are 2 elements. 1 power 1 equal to 1 minus 1. 1 power 1 equal to 1. But 1 whole power minus 1. Okay. Now here 1 and minus 1 given in this group under the usual multiplication is a cyclic group or not? Yes, it is a cyclic group because this is also one of the subset of imaginary of fourth groups of unity. Now, according to the group of the subset, that is the subgroup. Okay. Here 1 be the multiplicative identity, and inverse of -1 is -1. Now that is also 1 is there. Now that must be the verified here. There are two generators, 1 and -1. Now here the subgroup of this part is also a cyclic group. Okay. Now students, listen carefully. Now this theorem is very important in examination, final examination. Please note down. Prove that every cyclic group is an abelian. Prove that in examination, this type of question is given. Prove that every cyclic group is abelian, but the converse need not be true. Very, very important in examination. Okay. First of all, let G under multiplication be a cyclic group. A must be the generator. Capital G equal to generated A. Now, in the set of the notation as set of A power n, here n being the integer. This is the cyclic group of this set. Now, this is the notion of the cyclic group. Capital G equal to generated by A means set of A or bracket of A or square bracket of A, whatever it is. In less than and greater than, in between, represented as an element small a. So that is also, there are so many representations, so many notations of cyclic group. Okay, capital G equal to read as generated A. Now in the set of the notation as A power n, because here multiplication as the composition. Now set of A power n means n being the integer. Suppose x and there are so many elements. Now this set can also be written as set of A power 0, A power 1, A square, A cube. A power 0 means 1. A power n equals 2. That is also represented as the identity is here. Okay. 1, A power 1, A square, A cube, so on. In between, A power n minus 1, in between, A power n and A power m is also consisting of the elements given in this set. Okay. Now this set can be expanded as set of A power 0, A power 1, A square, A cube, so on, A power n minus 1. We are taking in any two elements, A power n and A power m. A power n element is, say, x. A power m element is y. Okay, there are two elements given in this group, that is x and y, or we are x and y be any two elements given in the cyclic group. X element is A power n and y element is A power m. And the power of the elements here, n and m, there are two integers here. Now here n comma m being the integers. Okay, now this is, sorry, this is not G, capital Z is there. Okay, now please just have to rectify this one. N comma B M belongs to Z, not G. Now suppose here x and y be any two elements given in the cyclic group. X is A power n into A power m. So this is A power n plus m. N plus m, when it is must be abelian, now it can be written as m plus n is there. By the commutative property, n plus m can also be written as m plus n. So this is A power m plus n. And at the same time, can also be written as A power m into A power n. A power m is y, A power n is x is there. Simply xy equal to yx. Now commutative property is satisfied. Hence G under addition. Now here, in particularly Z under addition is an abelian group. That's why here in the cycle group of the elements are integral power of the elements are integers with respect to addition, because Z under addition is also abelian. Hence n plus m equal to m plus n. So finally, here x comma y belongs to G and xy equal to yx. Commutative property, or by the already we know that G under multiplication be a cyclic group, and according to this property, commutative property is satisfied. That is called that cyclic group is an abelian group. That's enough. Simple proof is there. Simply just you have particularly keep in your mind, there are two elements given in this group. One element is A power n and another element is A power m. In between, set of A power 0, A power 1, A square, A cube, so on. In between A power n and A power m, there are two elements given in this group. That element is represented as x and y. Simply xy equal to yx is there. Therefore, that's why given the cycle group is an abelian group. But just you have to see what is the converse of this statement. Suppose group, when it must be abelian, that is not a cyclic. Okay? When it is a group, when the group is abelian, but it is not a cyclic, that is the converse. Now, especially just you have to see and refer, there are, especially in algebra, okay, so many theorems are not converse of the theorem, it need not be true. But particularly should not mention the need not. Now, particularly the converse of the theorem is not true. Suppose only in sometimes then it must be a true. Okay, but the converse of the theorem maximum times yeah, that must be not be a that is not a true. Okay, that's why even the group when it must be abelian when it is not a cyclic. This is the converse. How to write the converse? Let G be a group, then it must be abelian, but it is not a cyclic. That is the converse. Converse is also the just we must mention this converse of the statement. When the group is abelian, then it is not a cyclic. What is the example? Here, in the particularly ordered relation, Z2 cross Z2. There are Z2 cross Z2. Now, Z2 is the additive group of integers modulo 2. Z2 is the additive group of integers modulo 2. So, A, B, any one of the element given in the group. Now, when the group is abelian means order of A equal to 2 because integers under addition modulo 2. So, particularly element of the order is 2. Now, that is the non-identity element A in G. Suppose G is cyclic, A must be the generator, but element of the order is 4. Element of the order is 4. Okay, but because there is no element in G whose order is 4. Okay, whose order is 4. Particularly, modular element is 2, then the group of the order is 2. But according to that element, because there is no identity A in G is there. But here A must be the generator means 1 minus 1, I minus I. These elements are represented as imaginary fourth groups of unity elements. But A equals to 1, that is the identity is there. Suppose when A is an element of capital G is there. But A equal to 1, A equal to minus 1, these are all elements. But then the group of the order is 4 in the imaginary fourth groups of unity. All integral power of the elements represented as the integers. Power of the elements are integers. When the group of order is 4. But here particularly additive group of integers modulo 2, when the group of order is 2, that is not a cyclic, but it is abelian. Okay, that's enough. Okay. Now, just you have to see and refer students. Now, in this examination, especially define cyclic group, prove that every cyclic group is abelian. Is the converse true? Justify. Justify means give any suitable example. That example is Z2 cross Z2. Not it read as Z2 into Z2. Z2 cross Z2. Now this is the additive group of integers modulo 2 is there. Already you have to explain here what are the generators of a cyclic group. Now in a generator of a cyclic group may not unique. Okay. Suppose A be any one of the element G equal to generated A and G equal to A inverse. In the integral power of the elements is 1 and minus 1. Now, there are only here A must be the generator. The inverse of the generator is also a generator. Inverse of the generator is also a generator. Very important. Okay. In examination, fill in the blanks is there. The inverse of the generator is in a cyclic group. Dash. Generator, group, abelian, cyclic group. So you must mention the generator. Generator is also one of the answer. Choose your answer. Okay. The number of generators of a cyclic group. Now there are two particular theorems how to verify the number of generators of a cyclic group. Now already you have to explain pi of n generators, and one is the in an infinite cyclic group there are particularly two generators. Okay. Don't forget this one. In an infinite cyclic group there are two particular generators. That is A and A inverse. That is one of the theorem for the according to the concept of properties of generators of a cyclic group. Okay. Now there are two generators in an infinite cyclic group. That is also one of the important debate. Okay. There are two particular in the integral power of the elements. When they are not equal, two particular integral power of the elements, that is A power n and A power m. That should not be equal here. Here n not equals to particularly n not equals to m. Now here being the both are integers, n and m both are integers, but that is not equal. So there are different and distinct. Suppose there are that is A power n not equal to A power m is there. Now these elements are all distinct elements of capital G. Yes, and so on of the parties given the group cyclic group is infinite because A square, A cube, A power 4. There are so many elements are there. Conversely, this is the necessary part is also enough. Any two elements are not equal. When the integral power of the elements are not equal, but if both are integers are there and all the elements are different and distinct, so if the group is cyclic group is infinite. Now converse part is suppose suppose it is equal. The integral power of the elements are equal, but n not equal to m. Now there are two integers here. Suppose n less than m. Already in the introduction of this part of a cyclic group is what is that? N less than m is there. N less than m means m minus n is greater than 0. N can both sides are minus n is also applied here. N minus n is 0 and less than m minus n. And in the reverse side read as m minus n is greater than 0. Now generated element is also applied here in the cyclic group a power m minus n. That is a power m into a power minus 1 whole power n. Now this is a power n and a power n into. Now this is a power m. Okay. Now a power m equal to a power n. So substituting of in the replace substituting of a power m is a power n is also there, and second element is also a power minus n whole power n. So finally a power n into a power minus n equal to is there. Therefore, there exists a positive integer small r such that a power r equal to is there. Consider any least positive integer or be any one of the least positive integer, that is a power r equal to is there. Suppose we shall prove that capital G equal to what are the integral power of the elements in terms of a, that is e means a power 0 equal to e, a power 1, a square, so on, a power r minus 1. Here r represented as the elements of the set is in terms of r, a power 0, a power 1, a square, so on, a power r minus 1. Here r by the integral power of the element. Integral power. Now r must be the integer. Hence cardinality of G. What is the cardinality of G? Here a power n equal to e, replace n part. Just you have to observe is replacing of n by r is there. Cardinality of G equal to r is there. Now when it is less than infinite. Okay. Suppose here group of the element is say x. That element is represented as the integral power of the element is a power n. Here n being the integer. Just we know that. What is the division algorithm? Division algorithm is now quotient, dividend, divisor, remainder, and according to that relation is n equal to qr plus s. N equal to, this is the n, and in bracket of q is the coefficient, r be its s be its remainder, r be its dividend of division of this part. Now n equal to qr plus s. Here q and s both are integers. Now what about the remainder? Remainder condition is s lies between s is greater than or equal to 0, but it is less than r. When the remainder must be 0 or it is greater than 0, but it is less than, purely less than r is there. So this is the division algorithm condition. Applying in the division algorithm x equal to a power n, replacing n by qr plus s. Here the integral power of the element is a power n. That element is say x. A power n replacing, that is the value of division algorithm is qr plus s. This is a power qr into a power s. A power qr can also be written as a power r whole power q into a power s is there. A power r, we know that a power r is identity because cardinality of a equal to small r, and according to that a power r equal to e is there. E power q means e. E into a power s means a power s. Now here the condition is s is greater than or equal to 0, but it is less than r is there. When the group must be infinite if and only if those elements, those integral power of the elements are not equal. Here n and integral power of the elements are also not equal because those are integers. When the group must be infinite, B is any one of the generator. What is that? Here B any one of the generator is there. Now the generator of the element is denoted by here that element is small a and another element is generator. Suppose A must be the generator and the element is small b. So what is the meaning of this one? A equal to, in terms of P of the integral power of the element is P power n. The value is A according to this one. P equal to A power m is there. So here n and m particularly some integers. A equal to B power n. Suppose A equal to B power n is there. Replacing B value is A power m in this one. B power A power m whole power n. That is A power mn. So particularly A equal to A power mn means applying on both sides A inverse. That is A into A inverse means 1 and minus 1 is there. Okay, a power m minus mn minus 1. Both sides a inverse is also applied on both sides. So that value is a power m minus mn minus 1. That value is e. That is an equivalent to e. E can also be written as a power 0. Therefore, suppose comparing on both sides, m minus 1 equal to 0 and mn equal to 1. Either m equal to 1 or m equal to minus 1 is there. Suppose 1 into 1 equal to 1, minus 1 into minus 1 equal to 1 is there. Therefore, B equal to A or A inverse. So 1 and minus 1 is also replacing in this one. A equal to B equals to A power 1 or A inverse. But both elements are not equal. There are two particularly generators in an infinite cyclic group is A and A inverse. There are two generators of capital G. That's enough. Students, it's this is very most important concept. Prove that infinite cycle group are two generators only. Okay, in the examination, G and G be any one of the cycle group. Prove that in an infinite cycle group, only two generators in an infinite cycle group. That is also one of the question is given in the final examination. Okay, now this is very important concept, particularly, and see this one. These are theorems, but in the examination that is not necessary. But we must know that these four principles are here. G be a finite. Suppose when it is G be a finite cyclic group, means n greater than 1, G equal to generated A. Suppose any two distinct elements are not equal here, I not equal to J lies between 0 and n. An element of the order is n be the cardinality of the group. Okay. And at the same time, capital G equal to, these are all integral power of the elements. Hello? Any doubt? Okay. Now here G equal to set of E equal to A power 0, A power 1, A square and so on, A power R minus 1. Already these two are proved here. When the greatest common divisor, when here just you have to take in here A power D is also one of the generator of a cyclic group. Capital G equal to generated A power D. If and only if D is the relatively prime. Relatively prime means when the greatest common divisor of D and n equal to 1. That is the relatively prime or mutually prime, whatever it is. Okay. When the greatest common divisor of in between D and n equals to 1. Now, according to the generator is A power D. Suppose, first of all, you have to take in the capital G equal to generated A power D, G be a finite cyclic group. To do that, D is the relatively prime with the greatest common divisor of D and n equal to 1. And the converse part is when the greatest common divisor D and n equal to 1. And to prove that A power D is a generator of G. This is the third proof. Fourth one is the number of generators capital G equal to the number of positive integers. The number of generators of a cyclic group must be equal to the number of positive integers less than n and relatively prime with n is there. There are two proofs here. The third proof is also one of the important in final examination. Okay, now that's enough. Now this is also so many times are repeated here. 3.4.8 according to this one. Finite cyclic group of order is n and R lies between 1 and n. Order of A power R. A power R is the generator of the order is n by GCD of n and R. This is the meaning of GCD of n and R. Greatest common divisor of n and R. This is represented as GCD of n and R is greatest common divisor of n and R. With a finite cyclic group, when it the finite cyclic group of order is n and the remainder lies between 1 and n. Suppose R is greater than or equal to 1, but it is less than n. And what about the relation? Here order of A power R be one of the A power R is one of the integral power of the element when A belongs to G. Order of A power R equals to n by relatively prime of n and R. Okay, that's enough. Now this is also one of the important theorem. Just see and verify. Now this theorem is also very important here. Now according to this example, what is the Z at 12? Replacing of this formula, Z at 12 equal to n value is 12 is here. What is that? N value is 12 by 12 and 9. Remainder is 9 is there. Order of 12 and 9. Now what is that 12 and 9? GCD of 12 and 9 is 3. So 12 by 3 answer is 4. Now in the examination is given order of 9 in Z12. This is one of the bit is there. Fill in the blanks or choose any correct answer, multiple choice, whatever it is. Order of 9 in Z12. According to this theorem, just you have to derive this one. What is that? Already what is the theorem here? Order of a power r equal to n by GCD of n and r. Okay, here r equal to 9 and n equal to 12. Those values substitute and give this theorem. 12 by GCD of 12 and 9. So 12 and 9 GCD is 3. That is the common factor. Now here 12 by 3 equals to 4. Now that is the order of 9 equals to 4 in Z12. That's it. Okay. Now students listen carefully. This theorem is very most important in the final examination. Okay. Very, very important. There are so many times repeated here. Every subgroup of a cyclic group is cyclic. Already we have to discuss in the previous part. Suppose when the group is cyclic, then the non-empty subset of a group is subgroup. Subgroup of a cyclic group is also cyclic. Subgroup is also cyclic. When that group must be a cyclic group is there, then their subgroup is also cyclic is there. Okay. Now this theorem statement once I have to repeat here. Every subgroup of a cyclic group is cyclic. First of all, just you have to see here. First of all, given the group is cyclic. Cyclic group means any generated by a group is generated by an element of a group is cyclic. So just you have to mention here. G equal to generated A. Before capital G be a cyclic group. Now then H be the subgroup of G. Now first of all, at least one identity element is there. Given in this subgroup, subgroup is here to prove that subgroup is cyclic. Okay. Now first of all, what is the H? What is the H? H equals to generated E. E means identity. Okay. Given that subgroup is at least one identity element is there. And through that generated of E is also represented as either this one or this one. Only identity element must be generated in a subgroup. Suppose H not equal to generated E. Not generated means at least there is non-zero integer is denoted existence. Or B non-zero integer. Now any non-zero must be existence of the integer. Now then their integral power is denoted by A power R belongs to H. Now we know that in the infinite cyclic group is A power 1, A power minus 1. There are two finite generators. Suppose R being the integer means at the same time negative integer are also repeated here. A power minus R is also belongs to H. Therefore, there is a positive integer R and A power R belongs H and their inverse of the generator is also a generator. A power minus R is also belongs to H. And R be the least positive integer means such that A power R belongs H and least positive integer represented as lies between R must be the greater than 0 when be integer. Now A power R belongs to H. That is the least positive integer. We shall prove that that generated must be generated by an element of a cyclic group. Then its subgroup is a cyclic group. Means H equal to generated A power R. This is our proved part. Now A power R belongs to H and that generator is also contained or equal to H. Now in the next other side, X be any one of the element of the subgroup and that element is also given in this group. Okay, when it is the subgroup of the element, already that element exists given in the group. So that group of the element, generated element is generated A. So X equal to in terms of generated A means A power n. This is the represented as integral power of the element is A power n. Here n being the integer, that element is say X. And at the same time later we have to discuss in the above theorem. Now again applying a division algorithm n equal to QR plus S. S is greater than or equal to 0, but it is less than R. By division algorithm means in the lower class level. Here n is also represented, and this is S, quotient is Q, and this is R is also quotient of this part. Okay, Q be the quotient, R bits divided, and S be the remainder is there. N equal to QR plus S. Q and S being the integers, and S greater than or equal to 0, but it is less than or is there. And again, applying the generated part A power N equal to A power QR plus S. And again, A power QR into A power S, A power R whole power Q into A power S, A power R, A power S equals to, because A power N into, because already we have the existence this one, A power N, this value, into A power R whole power minus Q. Now A power N is, X is there, X into A power R whole power minus Q. Okay, A power N, A power S can also be stated as, A power S means A power N into, now this is A power QR means N minus QR. N minus QR equal to S, and applying on both sides A is there, A power N minus QR into A power S. So that's why A power S equal to A power N into A power minus QR. A power minus QR means A power R whole power minus Q. A power R whole power minus Q, this value is X. So X and A power R both elements are in capital H when H is a subgroup. Therefore, A power S is also belongs to H. By the least property, R and S cannot be positive. Therefore, S must be equal to 0 is there. S must be 0 means A power 0 is the identity is there. Therefore, remaining the form is when the S equal to 0, N equal to QR. Because when it is the least property, but it is not a positive, because S is less than R, that's why S equal to 0. So N equal to QR means again applying on both sides A is on the base. Integral power of the elements can be written as A power N equal to A power QR, because since S equal to 0. Now here A power N means X. A power QR means A power R whole power Q. So here the generator is A power R. Okay. Therefore, that generator is an equivalent to X is there. Now that is that generated by an element of a subgroup is there. So any generator is also, when it becomes the generator, then it must be generated given in the subgroup. Then the subgroup must be a cyclic. Now this is very simple proof. Capital H equal to generated A power R. Okay, that's enough, students. Now this is one of the important theorem in examination. Very simple question. Okay, in Z under addition be the one of the cyclic group in the subgroup of the form is under addition. What is the generator of this part? NZ. N being the element. Okay, NZ is also form of Z under addition, and this that subgroup is also any non-negative integer is N. So in the Z under addition of the subgroup is of the form NZ. Now that is the simple corollary. H be a subgroup of Z under addition. The by above theorem subgroup of a cyclic group is cyclic. H equal to generated N means now in additive notation as N into M. Here M being the integer. Now here M being the integer means that is NZ. Okay, that is NZ. We can take N is greater than or equal to 0. Generated of the element is X equal to generated minus N. Because in additive notation, inverse of the addition is subtraction. So N and minus N both are integers. So NZ is also integer, minus N of Z is also integer. Here N and minus N both are generators in a additive group is there. So that's why generated X equal to generated minus N. This is the above theorem of the subgroup of cyclic group is cyclic. Now through the multiplication and the addition part represented as the element is generated X equal to generated minus N, then its form is NZ under addition of this part. Okay, now this theorem is also see and refer in examination, particularly already we have to discuss the very important concept in the examination point of view. Now those theorems are very important. Cyclic group is cyclic, cyclic group is an abelian, and subgroup of a cyclic group is cyclic, infinite cyclic group of two generators, and those theorems corresponding to the definition and examples. Especially this class is also very important and essential concept in the examination. Okay. Now please keep in your mind cycle when it is the when it is understood the cyclic group of concept, now automatically generated in the finite. We must know that we will know that finite structural group theory part. Okay. Now this example is also so many times are also repeated here. Find all subgroups of Z24. Find all subgroups of Z24. Please wait for 10 minutes only. After the 10:30 is 11:30 is also closed this session. But one of the important theorem, Lagrange theorem, we will discuss after this example. Okay, don't forget this one. Now that theorem is also so many times repeated. That is the backbone theorem of group theory part and enter the algebraic part. Okay. Without Lagrange theorem, we can't expect anyone, and there are so many applications through the Lagrange theorem concept. Now, this is the final example. This is the one of the example to write the Z24 subgroups. Okay, find all subgroups of Z24. First of all, what are the divisors of 24? 1, that is the unit part. 2 is also divided by 24 divided by 2, and 3 divides 24. 4 divides 24. 6 divides 24, 8 divides 24, and 8 is also one of the factor. 12 divides 24, 24 divides 24. 3, 4, 5, 6, 7, 8. There are 8 divisors of 24 here. So, how many divisors in the Z24? There are 8 divisors. That they are 1, 2, 3, 4, 6, 8, 12, 24. 1 is one of the factor. That is the unique factor. 2 is one of the factor, 3 is one of the factor, 4, 6, 8, 12, 24. These divisors are also divides 24. Okay, these are also factors of 24, whatever it is. Now, Z24 subgroups is 24 by 1. It can be subgroups are denoted by generated 24 by 1, generated 24 by 2, 24 by 3, 24 by 4, square brackets, you must look at it as square brackets, 24 by 6, 24 by 8, 24 by 12, 24 by 24. Now, this value's remainder is 0. 24 divides 24, okay. So, generated 0 represented as generated 0. This is how many times cancelled? Box of 12. This is a box of generated 8, generated 6, generated 4, generated 3, generated 2, generated 1. Okay. Now, Z24 of the subgroups are generated 0 means 0 must be the generator, 12 generator, 8 generator, 6 generator, 4 generator of 24, 3 generator of 24, 2 generator of 24, 1 generator of 24. These generators means represented as the subgroups of Z24. Now that is very simple. Now we have to practice and some other also practice, see in the end of this part and case study and check your answers once again. Some other short answer questions are also given in this exercise. Okay, now that's enough. And see this one of the important theorem just you have to see here. And after the completion of this one, tomorrow we will discuss some other concept. Please stand the line. Now, thus already you have to explain here. Define cyclic group. Prove that every subgroup of a cyclic group is cyclic. Now, according to this one, and entire the completion of cyclic group part is there according to this question. Okay. Next one. Now, this example just you have to see and refer. State and prove Lagrange theorem for finite groups. In examination is given. State and prove Lagrange theorem for finite groups. This theorem is very, very important. Tomorrow we will discuss cosets of subgroups, and according to the cosets, we have to explain the Lagrange theorem. But now today is also one of the important concepts just after the completion of this theorem. Now end of the session, then it must be closed here. Now end of this session. Okay. Now just you have to answer. Question is state and prove Lagrange theorem for finite groups. Please stay on the line. Now first of all, when the group must be a finite. Okay. Please listen carefully. Without finite group, we can't explain the Lagrange theorem. Now, only for finite group of the concept is we will discuss the theorem is Lagrange theorem. When the group must be a finite, it is consisting of the elements. Number of elements is finite, so that is called a finite group. Now, according to the finite group, we will discuss the one of the best theorem. The best theorem in algebra is Lagrange theorem. Suppose H is a subgroup of a finite group G. G under multiplication will be a finite group, and HB a subgroup of G is there. And now what is the concept? Now the statement of Lagrange theorem is the order of the subgroup, the order of the subgroup of a finite group capital G divides the order of the group. This is the statement, students. This is not the proof. This is the statement. Order. If H is a subgroup of a finite group G, then order of H divides order of G. That is one of the statement. And this statement can also be stated as the order of the subgroup of a finite group capital G. The order of the subgroup H of a finite group capital G divides the order of the group. Divides the order of the group. Simply notation as order of H of a finite group capital G divides the order of G. Order of G means order of the group. Order of H means order of the subgroup of a finite group G divides the order of the group. That is the simple statement. That is the Lagrange theorem. So first of all, select G under multiplication be a finite group. Now this is the rough concept. When the group order relation is circle from G cross G to G, this is the cardinality of the group is mod G by mod G by mod H. Okay, mod G by mod H, and that's mod H divides mod G over R. Okay, and mod H is a divisor of order of G. Okay, there are so many expressions here. Now, order of the when the group of order is say N and subgroup of the order is M. Now we must define order of G and H means G comma H. This is the cardinality of GH equal to cardinality G by cardinality of H. Now this is also one of the important bit, students. Now this is very important expression. Mod G of H and equal to mod G by mod H. O of G and H equal to O of G by O of H. This is also one of the fill in the blanks. Now order of G is N and order of H is M is there. Just you have to see here. First of all, select G under multiplication be a finite group. Group of the order is N and group of the element is say A. Now this is cardinality. This is the order of the group, whatever it is. Now there are so many elements of A is there. A1, A2, so on, AN expressions. Because group must be a finite. Suppose HB a subgroup of G is there. Now those subgroup of the group of the elements combining with the subgroup, and now it can be decomposing with at the right side and left side. Now subgroup of the elements with the subgroup coincides with the left side, that is the left cosets. AH, B is also one of the elements given in the group of the subgroup is BH, CH. Now these are all left cosets. And group of the elements is A, B, C, and so on. Now those elements coincides with the subgroup is HA. Those elements at right side of the subgroup HA, HB, HC. These are all right cosets. Okay. Now tomorrow also we will discuss the cosets part is also there. Okay. Now here small h and capital H means this is the left coset. Subgroup of arbitrary element at left side. Small HB belongs to capital G and that is also capital H. Now that arbitrary element coincides with the subgroup. This is the left coset. Now that is the form left coset of the form is so that element is also represented as X is there. XH is also left coset. Now this is HI elements coincides with the subgroup. Elements is H1H, small H2H, H3H. These are all left cosets. Here small h be the arbitrary. Now these are all right cosets. Capital H and small h. Small h is also represented as small x, hx. This is also right coset. That is set of h and small hi, hh1, hh2, so on, hhn. Okay. Now there are two types of cases given this proof of the theorem. First case is when the orders must be equal. Group of the order, subgroup of the order, when it must be equal. Now we are nothing to prove. Directly theorem is also obviously. Because order of the subgroup of a finite group divides the order of the group when the group of the orders, group and subgroup of orders must be equal. That is nothing but proof. Because order of H divides order of G. If it is not equal, that is the second case. This is the necessary part and this is the subject part. This is the case one, first possible part. When it is equal of their orders, but it is not equal. So group order is n, subgroup order is m, but it is not equal here. And ai elements given in the group a1, a2, so on an. Number of distinct elements given in H is entirely different from capital G. Entirely different from capital G because the orders are different. Group order is n, subgroup order is m. Here n and m are different and distinct elements given in this group. The subgroup can be decomposed of an elements of G. It can be divided into left cosets and right cosets. Already explained given in this part. So all the cosets must be represented as H contained or equal to G is there. So capital mod G order of G equal to order of HA plus order of HB plus order of HC plus so on order of H. Then the group of the order must be equal to the sum of all the cosets of the order, including with the subgroup of order. So mod H is an equivalent to when the subgroup of order is M, all the cosets of the order is also same manner. So a group of order is N and some cosets order is also same, and it continuing the process of the subgroup of order m plus so on up to k times. So n equal to m plus up to k times means n equal to k into m. So n equal to km means k equal to n by m. So replacing n by mod G and replacing m by mod H. Therefore, k means order of G by H. This is the index of the subgroup of a group. It can be stated as mod G by H means index of the subgroup is H in G. Index of the H in G means order of G by H or mod G by H equal to. This is the square bracket of G from H. G hyphens of H. Now this is the upper and lower part. This is the hyphen G from H. Now H in G, whatever it is, this is the index of H in G. Means order of G by order of H. Now this is also one of the important bit in the final examination. Either fill in the blanks or choose your correct answer, multiple choice. Order of G by H equal to order of G by order of H. Okay. Now in the examination, order of G minus order of H, order of G plus order of H, order of G by H means order of G by H equal to order of G divided by order of H is there. So the values G by H index of the element is K equal to N by M. Group order is N, subgroup order is M. Finally, the order of the subgroup H of a finite group divided the order of the group. The order of the subgroup of a finite group G divided by divides the order of the group. Now that is the Lagrange theorem for finite groups. Okay, students. Now this concept just see and refer more times. Number of times are also repeated here. Now just you have to watch number of times, especially this session. Today's class very important and yesterday class is also very important. Now all those classes are number of, just you have to refer the number of times, just see and watch, and just your understanding capacity, especially in subject point of view. Okay, thank you one and all students. Already time is over. Thank you one and all. Wish you all the best. Wish you good luck. Tomorrow we will meet again, same timing and same class. Okay, wish you good luck and wish you all the best. Thank you. Please stay on the line once again. Just you have to see it. Students, any doubts? Students, please respond immediately. Any doubt here? Okay, thank you. Tomorrow we will meet again, same timing. Okay, and we will discuss more topic here. Thank you. Thank you, Vanessa.